So today's class will cover one of the cryptographic primitives that is known as a hashing function. So I will show you how this can be used from a programming language, give you some practical skills with it. But before we do that, I will tell you a few things about what hashing functions do in principle and why they are necessary. So you could treat it as a mathematical function that takes some data at the input and it gives you a fixed length output. And let's say fixed length, it means that it always has the same length. For example, 16 bytes or 20 bytes. Or we could imagine a hypothetical hashing function that gives us a 4-byte hash. And when I say arbitrary input, it means that the input can have any length. It could be empty. It could be 1 character long, or it could be 50 bytes. It could be 50 gigabytes. It could have any length. In any case, you will always get a fixed length thing at the output. This output is usually called a digest or a hash. This function has several important properties. The first one is that it's a one-way function, and you see the arrow going from one side to the other, but not the other way around. This means that I can produce a hash from an input, but I can never produce the input given its hash. Another property is that for the same input, it will always give us the same hash. By definition, that's how it behaves. Another property is that if I change at least one thing, at least one bit in the input, it will give me a completely different output. And remember, we spoke about integrity in classes, how we can figure out if something has changed. Well, hashes have something to do with it as well. There is one, it should be obvious from what I mentioned so far, or maybe not. So the thing is that when you change something in the input, it gives you a completely different digest, such that it's not different in only one bit, but it's different in as many bits as possible. You could put it this way, or in another way. If I flip one bit at the input, then the probability that all the other bits in the output will be flipped is 50%. As opposed to the digest for the previous input where that bit had the opposite value. So from this point, we can already say that there is a unique hash for every string or every input set you could come up with. Do you agree or disagree with this statement? Yeah, so I'm going to repeat your statement because this is not heard in the screencast. So one person disagrees. Why?
I disagree because taking hypothetically there is a lot of inputs, but there's only limited output string. I mean, if we have, I don't know, our string, the output string is 16 bytes, then there's a limited amount of string of this type, so, but the amount of input is infinite.
Mm-hmm.
Really, really large comparing. So if we map, then we just cannot have the
can't have two strings that map to the same hash.
Okay, so what was said is correct. I'm going to rephrase that for the screencast and do some graphical illustrations as well, and then we can switch to the practical stuff. So to illustrate this easier, let's imagine a hypothetical hash function that gives us an output that has a 3-bit length. So all the digests we produce are 3-bit long. How many digests are there in principle? Which is approximately 8, depending on the speed of light. And so there's 1, 2, 3, 4, 5, 6, 7, 8. The set of possible digests has the cardinality of 8. So it has 8 elements in it. Now, this set on the left side represents the possible set of strings we could come up with as input for the hash function. So I have 1, 2, 3. Actually, there is an infinity of texts I could come up with and feed them into our hashing function. This means that for any string in this set, there has to be a mapping to one of the possible digests. And since we have infinity over here and we have only 8 items there, then there is a thing called a collision. It refers to the situation in which you have one string and another string which are both mapped to the same digest. So it's easy to illustrate here when we only have 8 digests, but typically a hashing function gives us longer outputs. For example, something that is 160-bit long, or 256 bits long, or why not 512. In this case, you have this many digests to choose from. That's a huge number, and it's even bigger here. But still, we must face the fact that in theory, one can find a multiple number of inputs that will give us the same output. And this is called a collision. Now let's do some experiments with hashing functions. I'll be using Python, but you can use whatever language you want. And feel free to start Python right away and type along with me. And we'll check out the hash function in action. As of a certain version of Python, these functions are kept in a library called hashlib, so you can import that. An easy thing to do is this. This module has a class MD5 that corresponds, it's an implementation of a hashing algorithm known as MD5, and it stands for message digest. Prior to that there was MD4. This one is not safe for use these days because there are papers that published approaches on how to come up with a collision in a much easier way than brute forcing one by one and trying until you find that collision. But let's get back to this. So the first thing you do is you import your module. And then you can call functions from it. So let's see. You can call it like this. It gave us a hash object which exports a bunch of functions. What I didn't do is I did not capture this output somewhere, so I'm going to do this. If you type hex digest, it's a function of an MD5 object. It prints you the digest in a human readable form. And you see this string, it's a hexadecimal representation, but you can also call it like that, and then you see just a bunch of bytes. If you want to know the length of this digest, you could do it like that, and it says 16. So it means that the MD5 algorithm gives us digests that have 16 bytes in length, and that's how many bits? If you multiply by 8, it's approximately I will leverage There are other algorithms. For example, SHA, which is actually a family of algorithms, SHA-1, SHA-2, and not that long ago, well, last autumn, SHA-3 came to exist. SHA stands for Secure Hashing Algorithm. It's a choice made by NIST, which we brought up earlier in another class. It's an organization responsible for choosing and standardizing certain algorithms, among other things. So every now and then they create a competition, which is an open event. Anyone can participate. Any group of scientists, mathematicians, or qualified people. So what NIST does is that they set forth a bunch of requirements. We need a hashing function that produces a digest of that many bits. It must have the following properties. It must comply with the following performance requirements and the following security requirements. And then every team that participates proposes their own algorithm. Then there is this analysis phase in which every contendant in the process is reviewed, and then after several iterations they choose one of those algorithms and they turn it into a standard, which is NIST is an American organization, but their recommendations are made public, so anyone could stick to this guideline. SHA-1, SHA-2 are currently in use, but just to be sure, because they anticipated the development of technologies and progress in cryptanalysis, which is reverse engineering algorithms and looking for weaknesses. So they decided to open a competition for SHA-3, and last year they chose an algorithm which was originally called Kechak. You spell it with double C, but you're supposed to read it as Kechak. And it became SHA-3 these days. So let's have a look at this example. I wrote the string test, and the digest for that was this. I am going to change one letter, QRSTU. So instead of the last T, I'm going to write a U, and I call this function again. Now compare this to that. First of all, they are different. Second of all, we notice that the difference is not just in one character. And it's not a difference that could be called a neighborhood difference. For example, this digit was 6, but now it's 7 or 5. No, it's completely different, and that's the point. When you're dealing with really long amounts of data, you could, of course, do it like that. Keep typing. Notice that no matter how long the input is, the output always has the same length, as we have discussed previously. Let's try an empty string. Still, it gives us an output. And if I give it the same input again, it gives me the same output, which is another thing that is by design. If any of you tries to MD5 hash an empty string, by definition, if your implementation of MD5 doesn't suck, you will have the same thing. So go ahead and try it right now so we could check if this really works. Okay. But if I had to hash a 5 GB file, it would probably be really tiring for me to type it like this. So for that, you can try something else. So let's have an object, let's call it hasher. And let's see which functions it has. In Python, you can do it like this. Dir, and then you give it the object at the input, and it gives you a list of attributes and functions that object possesses. But in this specific case, I'm using IPython, which is a really nice Python wrapper, which gives me tab completion. There is a function called update. So let me set it to TE first. So this object has a state, and I've updated that state with this input. Now I can update it again with the string st, which is yet again updated. So now I can do this, and it gave me the hash in exactly the same way as if I did. Okay. You see, those strings are identical, which is by design.
Și voi, bună ziua, bine ați venit. Anul ăsta e foarte complicat pentru voi, credeți-mă, și asta o confirmă experiența colegilor voștri din anii precedenți. Și eu aș vrea ca voi toți ajungeți în luna iunie și să vă mânăm diplomele atunci. Asta e dorința mea. Dar le-am deschis cum să iasă. Ați avut timp să vă gândiți la teză de licență și probabil săptămâna viitoare vom fixa ziua în care vă vom împărți tezele de licență, ok? Dar ar fi bine săptămâna asta poate să ne întâlnim. Eu am să văd, poate pe miercuri sau joi, să stabilim o întâlnire. Domnul Tare, nimeni să veți în a doua parte. Dar bine că ne-ați luat aminte, am să vin și joi, atunci o să discutăm exact cum împărțim sașii și cum va avea loc toată procedura. Și acum vă pregătim că săptămâna viitoare vom fixa deja ziua în care vom împărți sarcinile pentru teza de licență. Mai aveți încă timp câteva zile să vă gândiți, veniți voi cu propunerile voastre, noi le vom critica și vom spune e bună, nu e bună și ori o acceptăm, ori o propunem altceva. E clar? Da, și gândiți-vă, avem acum un nou robot, așa că dacă cineva vrea să-și încerce puterile cu un humanoid, avem și teme de licență și pe tema asta. E clar? E deja la universitate, botezat și și așteaptă să fie domnul decan să fie torturat, testat. Acum o cheamă? Cred că un Max, dar să vedem. Primul care l-a descoperit e Petrușca, așa că îl botezăm numele lui. Da. Deci gândiți-vă dacă aveți idei și acolo. Bun? Este și așa o posibilitate. Bun.
So what we've observed so far is that I can either give it the whole input from one call and it gives me the hash, or I can feed it the input piece by piece and it still gives me the same hash. Now, if I had to hash a 5 gigabyte image, let's say it's a really, really long file, I could read it chunk by chunk. So while there is something in that file, I could read a chunk, I could update the hash, and then when it's all over, I can get the digest and I get the same output. It's guaranteed. I must also point out that depending on which language you use, the API may look somewhat different. For example, sometimes you should start with a function called init, then you call a function called update, and then you call one called finalize. And beyond that point, you can get the hash. So it's up to you to read the manual for whatever language or API you're using, and then find out how the calls are supposed to be made. Do you have any questions so far? All right. Has everyone tried to start a hashing function and did they all get the same hash for the string test? Okay, that's good. Did anyone try it in something outside besides Python? And did you get the same output? What did you run? JavaScript? Okay, JavaScript and PHP gave us the same output, which is a good thing. So, up to this point, I showed you how to use this primitive. But it's up to you to think about ways in which it can be used as a building block in a bigger thing. And we'll discuss that a little bit later. But for now, you have to do several things. Hash a few different strings, play with the function, see what kind of output you get. Try a few other algorithms. So besides MD5, HashLib has a few other things to offer. For example, this or that or that. Hash the same string with different algorithms and see what happens. Do you think the hashes will be the same? Somebody said no, but why? Yeah, they indeed will be different, and that's a good thing. Sometimes you might notice it on websites when they publish a downloadable ISO image for a new flavor of Linux, they give you an MD5 hash of the image as well as an SHA1 hash of the image, so you could really double check if it wasn't tampered with. Now, if you download a file and there's a hash mismatch, what does that imply? Okay, so the obvious conclusion is that the file on the server is not the same as the file you've downloaded. Or the file on the server is the same as yours, but somebody modified it but left the hash unchanged. You might also notice that hashes are used by BitTorrent clients to hash individual pieces of files that are being transferred. And by files, I mean, of course, legally purchased movies and audio albums, nothing illegal. What are your questions up to this point? All right, so if there are no questions, I'm going to switch to the actual major assignment for this class. But until then, your mini assignment, so I will check all of your computers and I want to see on your screen certain things happening as a proof of the fact that you really tested a hash function. So your mini assignment will be as follows. Show me how you show me the hashes in MD5 and SHA1 for the following strings. Test, an empty string, and here be dragons. Then you have to tell me which hash is the longest and and then show me the hash of their bit dragons, which has only the heading distance between those two strings is just 1, but their hashes will have some relationship between them. Maybe, maybe not. You will tell me. And once the mini assignment is complete, we switch to the next phase of this class.